Hey guys, it's Mr. Lowry. We are coming back to revisit these theorems here that we talked about last week because we didn't prove them yet. And today we're going to actually get in there and prove them. I think it's kind of useful to use them first just so you can kind of get the idea and then kind of go backwards and prove them from there. So that's kind of our strategy. Now this is on page 504 of your textbook. So if you want to, reference this or whatever while you're doing your homework, that's where it is. But what I wanted to point out to you here, again, and just kind of refresh, is that there's 4 theorems here. Sorry, my hands got like marker all over them because I've been doing a bunch of problems on the whiteboard. But there's 4 theorems here that all relate to this kind of setup, this shape here. So what we have is parallel lines, and they're cut by a transversal. Transversal is a line that crosses 2 lines. And then we have all these, angle relationships. So when we have this setup, we have 4 results that follow. Notice that the hypotheses for all of these theorems is the same. If 2 parallel lines are cut by a transversal, 2 parallel lines cut by a transversal, 2 parallel lines cut by a transversal, 2 parallel lines cut by a transversal. So these are like our basically our parallel line transversal theorems. There's 4 of them. We got the corresponding angles theorem. So if these lines are parallel, then like angle 1 has to be congruent to angle 5. So there's a little bit of glare there. Angle 2 has to be congruent to angle 6. Angle 3 has to be congruent to angle 7, and 4 has to be congruent to angle 8. That's what the corresponding angles theorem says. And when we talked about this theorem initially, we talked about this like corresponding like corners. So if these are 2 streets that are parallel, and this is a 3rd street that crosses both of them, and these are like intersections here, notice that angle 1 and angle 5, they're both on like the northwest corner of the intersections. So those are corresponding angles because they're like kind of on the same corner. Angle 2 and angle 6 are corresponding angles because they're both on the northeast corner of the street. Okay, so that's the first one. Alternate interior angles. Alternate means they're on opposite sides of the transversal. They're also on opposite lines, so like they're kind of kitty-cornered to each other. So 3 and 6 are alternate interior angles. Interior means they're on the inside of the 2 lines. So 3 and 6 are alternate interior, 4 and 5 are alternate interior. So according to the alternate interior angles theorem, 3 is congruent to 6, 4 is congruent to 5. Okay. And then we have the alternate exterior angles theorem. Exterior means on the outside of the 2 lines, and alternate again is opposite sides of the transversal line. So we have angle 1 congruent to angle 8, and angle 2 congruent to angle 7. And then the consecutive interior angles theorem. Okay, this one's important because this is the only one that the conclusion doesn't have congruent in it. The first 3 angles are congruent, angles are congruent, angles are congruent. This one is angles are supplementary. So in this one, consecutive interior still means inside the 2 lines, but consecutive means like next to each other. They're on the same side of the transversal. So angle 4 and angle 6 are supplementary, not congruent. Angle 3 and angle 5 are supplementary, not congruent. Okay, I wanted to talk a little bit about the order of these theorems and how we prove them. If we get this one, we use this theorem to prove all 3 theorems. And I'm going to show you guys those proofs today. So this is the most important one. And once we prove this one, this and this and this all use this theorem. What I wanted to bring up a little bit or point out to you is that this one right here, consecutive interior angles theorem, is the converse of Euclid's 5th postulate. Okay, Euclid's 5th postulate, if you recall, says if these 2 angles, like 6 and 4, add up to 180, then these have to be parallel. This says the opposite. This says if these are parallel, these have to add up to 180. So what Euclid did is Euclid took the converse of this one to be true as a postulate, as a common notion. And then he proved the converse of this one, the converse of this one, and the converse of this one. So he kind of went in the opposite direction that we're going to go. He started in a different spot with a different postulate, and then he proved the converse of these. So we're kind of branching off a little bit because we're going to start here. And it's interesting because in some books, this is actually called a postulate. People don't call it a theorem. They just say, hey, this is obvious. So I'm going to show you some reasoning behind this one. We're not exactly going to prove it because we don't have all the information we need to prove it just yet. And if you'll notice, the proof here is non-example 550. Well, we're on page 504. So in 46 pages, we'll have the information we need to prove this. But it's still important to talk about initially so that it makes sense where this comes from so we can get the other three. So let's take a look at that really quick. Okay? So here I have the corresponding angles theorem written out. All right, two parallel lines cut by a transversal. So if these two lines, L and M, are parallel, then angle 1 is congruent to angle 2. That's kind of the theorem here. All right, so before we, talk too much more about that, I need to teach you something about what's called a transformation of a shape. Okay, so later, in one of the later chapters here, we're going to talk about what we call transformations. Okay, there's lots of different transformations, but the three kind of key ones, or the three like fundamental ones, are reflection, rotation, and translation. Okay, so what I'm going to do is I'm going to transform this shape here, and I'm going to use this clear piece of plastic to show that. So what I'm going to do is I'm going to copy this guy, and we'll label the points A, B, C. Okay, and there's three different transformations that we're going to talk about. Translation, reflection, rotation. Okay, so a translation is basically just a slide. You take a shape, and you can do this like in the coordinate plane, like on a grid, and you just move it. That's a translation, right? Or you can, you can go down, or you can go at an angle, whatever. That's all a translation is. Okay, it produces a similar shape, a congruent shape, just in a different spot. So that's a translation. A reflection is when you like flip it over, so you get like a kind of a mirror image, and it also kind of moves as well. So there's a reflection, or you can reflect it like this way. You can get like a mirror image. Okay, and then there's rotations where you can spin it, right? So there's like a 90-degree rotation. There's like a 180-degree rotation. Okay, so that kind of thing. And we kind of did something similar to this in one of our activities in class one time. But yeah, there's a translation, reflection, which is like a flip, and a rotation, which is like a spin. And we'll talk all about those in like the next chapter, so a chapter coming up. But here's the important idea that we need to prove this theorem, or to talk about this theorem. When we do any of these three things, we preserve angle measurement and segment length. So, for example, if I slide this is still the same length. This is still the same length, and this is still the same length. Also, angle A is still angle A, and angle B is still angle B, and angle C is still angle C. I haven't changed those. So these three transformations preserve lengths of segments, or lengths of these three lines that make up this triangle, and also the angles. Okay, so that's the important idea. So what we can do is we can take a line, and we can translate it, and we can show that this corresponding angles theorem is true. Okay, so here's what we're going to do. We're going to take a line, and we're going to draw kind of like a transversal. Okay, and what we want to do is we want to copy this line. We want to translate this line. So what we're going to do is we're going to use our little plastic thing again, and this is the line that I want to translate. So I can slide it up or down, or left or right. What I'm going to actually do though is I'm going to slide it in the direction of this line, this other line. So this is the red line is the one that I'm going to translate, and the blue line is the direction. So by moving the line and keeping it lined up with the blue line with where it was copied from, we get, you know, a translation there. So this line is just a translation of this line, right? It hasn't really changed at all. It's just kind of moved position. What we know is that these two lines have to be parallel because they're the same distance apart, right? When I moved the line, I moved every single point on the line. So every single point moved the same distance, which means these lines at every point are the same distance apart, which means they have to be parallel. The other thing we can guarantee is that when we translate, all of our angle measurements are preserved, right? That's one of the properties that we talked about of translations. So if I extend these a little bit, you'll see that what I have is two parallel lines cut by a transversal. So we use the idea of translations to create the shape that we're after, and we know one of the properties of translations, I'm going to try to write some numbers here, is that angle measurements are preserved. So this angle started out, right here, this angle started out as angle 2, but when I translated it, it's still the same angle that it was before, it's just in a different spot. So this is the same angle as the original one. So these two guys are basically their corresponding angles. Okay. So going back to this guy, we can think of line M as a translation of line L, right? We start with this angle here and this line, and we just translate it up, and we get this angle. This is just a translation of angle 1. And we know that the angle measurements are going to be preserved. So by doing that translation, we guarantee two things. We first guarantee that these are parallel, and we second guarantee that these have to be congruent, because the property of translation is that it preserves the angle measurement. So that's kind of where this guy comes from, the corresponding angles theorem. Now, that's a little bit different of a proof than we've done in the past. It's a little bit, different format, and it's not, a two-column proof. Some books that you're going to look at call this a postulate. They just say, hey, look, these angles got to be the same. It's obvious, right? They have to be. Or they talk about that translation idea and say, look, if you can take a shape and translate it onto another shape and they're exactly the same, then they have to be congruent. So they use that definition of translation or properties of translation to get this corresponding angles theorem or corresponding angles postulate. This is the big boy. This is the super important one for today, because all the other three, the alternate interior angles theorem, the alternate exterior angles theorem, and the, I always read this one, the consecutive interior angles theorem, they all come from this guy, right? And the point I want to stress is that whether we start where Euclid started and work the direction he worked, or whether we start here and work backwards, we get similar results. So that's kind of the justification for the corresponding angles theorem. You can also call it the corresponding angles postulate if you want. The next 3 videos are going to be the proofs of the other 3 theorems, and they're going to use this theorem.